Hello everyone, and welcome back. In this video we're going to talk about emulation accuracy. Now, it is not something that we need to worry about all the time. I'll say 99% of the time, probably even higher. We don't even need to worry about that much, but it is something that we need to keep aware of whenever we're making a game on an emulator. But with all that said, let's get started. Alright, so in this video we're going to cover a niche topic, which is our emulation accuracy. That is something that we have to keep in mind whenever we're going to make a game, and we decided to use an emulator instead of our actual console to make our games. Now, an emulator job is basically to behave or to act like another system. So the job of the Zelda emulator that we've been using to run our Atari 2600 game is to behave like an Atari 2600. And that is pretty much the whole job of an emulator. And here is one quick example of me just running the Zelda emulator to run our Atari 2600 games, and as well our game Combat Disc that we made from the previous videos. And of course, it doesn't mean it is just the Atari 2600. It can be the Super Nintendo. You can use your computer to emulate a PlayStation. You can even use it to emulate a Magnavox Odyssey, which it doesn't have a CPU. You can just emulate the gates. And it doesn't stop there. You can use it to emulate your phones. If you ever use any Android SDK, you have an emulator there, so you can use it. So your computer is emulating a phone. And it can be even crazier than that. You can have your computer emulating a phone, and your phone can emulate another console. Like probably there's another Atari 2600 emulator on the store right there. You can download it and you can run that on your computer. So it's like an Inception-like emulation going on. And of course, it can even be another system like I old MS-DOS with DOSBox. So, and it doesn't necessarily mean to be the computer. Can run like I said, the phone can emulate that. And as long as you can try to have one system, whether it being a computer, whether it being a console game, like you have a PS4 emulating a few PS3 and older games, or PS2 games and so forth. It can be a cell phone and so forth. One system, try to imitate another system. However, since we're talking about emulation, which is pretty much an imitation, so you're trying to imitate what another person do, you can imagine a scenario where you give a certain input for both for yourself and the actual copy, and the output is going to deviate. And that's where the whole subject comes about accuracy. So giving the same input for both the original part and the emulation part, it might give you a different output. And that pretty much happens because of unpredictability. And that's something that we're not expecting to happen. There's plenty of memes on the internet about the user interface, how you design something in mind and then the user do something completely unexpected. And for example, let's say you're making a game, and let's say for Super Nintendo, or why not, it can be the Xbox 360. And then you're playing a game and somebody just unplugs the controller. Something unexpected happened. And how can you, as a programmer, make up for those user cases? And how can the emulator behave exactly like the console would behave in that situation? So it can be the user, can also be different hardwares. It's not even like if you think about the PlayStation 4, and then there's later the PlayStation 4 Pro, which there's a case where I think the game was called Day Gone or something like that. I haven't played the game, so I'm not really sure, but I know when it came out on launch day, it was having a lot of bugs on the non-Pro version, so it was really tested on that versions and was causing a lot of problems on the normal versions. So if they had problems with the hardware, imagine if you're making an emulator for the PS4, you have to put those bugs, well, before the update, of course, on the actual emulator, so it behaves just one-to-one and the exact same results. So given the same inputs, you have to give the same results, even those glitches. And it's not really just completely different hardware like the PS4 Pro. The Atari 2600 went over. We have the Heavy 60 was the first one, and then a lighter 60 next to it, which was a lighter version with less. They always trying to make the console cheaper, so that's why. And then you later on you have like the Vader sleek ones, and that goes through all consoles. Like the Switch has, even though there's a Switch Lite, even before then they're always trying to make it cheaper and lighter. And they can also be just because of the behavior of the chipset itself, like the R6502 that are being working so far. Whenever you use those illegal opcodes, that's unpredictable behaviors. There's a few of them that people can guarantee for, like 3 of them, but it's not something 100% guarantee. If I use this illegal opcode, it will behave 100% of the time. So that's some of the things you have to watch out for. Alright, so here I am under the video game emulation wiki, under the fandom.com website. And here is the main meaning of accuracy, is how accurate the emulator is to the original hardware. So given the same input, you have to give the same output from the game or the source code from the hardware, which is the benchmark that we're comparing to, has to give the same output. And depending how well this accuracy is, you're going to rank them different. So there's different types. You have a low, medium, high. You have a cycle and a circuit, sometimes called dice. And also have a sub-cycle, and even the other one is called the chipset accuracy. And I'm going to go over all of them. I know there's more on the wiki page, but I didn't want to open a bunch of tabs over here, which are the other, and I'm going to put the link of that one as well over here. But I'm going to be using the Super Nintendo emulator, simply because there's a bunch of them for the Windows, which there isn't that much for the other ones. Not enough for the Atari, not enough for the Nintendo 64, PlayStation. So there's so many of the Super Nintendo that's going to fit the bill, because it does not only has a bunch of them, has a bunch of cycle types. You have your cycle complete, you have high, you have the medium, and you have the low. So I'm going to show you guys all of them, as well for the mobile and the consoles over here, as you see over here. So there's a bunch of them, that's what I'm using. And if you come all the way down here, right over here, if you click on this article over here, it's going to show over here this page. Well, this is basically saying what this is saying right over here, which I passed over. So more accuracy means less glitches, but it means a lot more CPU power, which is that's why this graph is showing over here, more power. But it does show here a picture of the difference of types. Here you have a higher accuracy emulator to the left to the right. So this is because this one is rendering the shadow and this isn't, according to the article. Well, there's a video over here of a high and low accuracy emulator being displayed. So here you have the ZNES over here, which is considered a low accuracy emulator, which is surprised me because this is the emulator that I used as a kid. I never noticed, but here it is. And you see BNES is a high cycle accuracy emulator. So you can see a video over here. And I'm going to be using The Legend of Zelda because it is an accuracy video over here. And I do own this cartridge. So we're going to show you guys the game running on my CRT TV with the Super Nintendo running compared to the emulator. And if you're wondering how this accuracy are given, there is a SU test for them right over here. Accuracy test. And here you have all the emulators that they ran and which one passed, it didn't pass this test. And here is the version as well. So with all that said, let's just go over here and let's go over all the types of the emulators that we have. Alright, just to show you guys, I do have the copy of The Legend of Zelda for the Super Nintendo as a focus right over here. And what I'm going to be doing is just, like I said before, just going to compare the runtime of the emulator to the actual console. And that's me right there to the left to show you guys that I'm actually running on the console. But I'm going to be using a hardware to extract all the data, all the video format. And just going to show you guys the left side and the right side, so the comparison between the console and the emulator. Alright, so here, before we start going over all the type of accuracies, I set up this little setup over here, so it should be a little bit more visually digestible. On the left, we have our console, which I use my hardware to extract the video from my Super Nintendo. And the right is going to be the emulator. So in this case, it's a high accuracy emulator, which is going to correspond to the BNES. And I'm going to play this video side by side over here, and you just try to see the difference. And then after you see the video over here, I'll go over how I set up this small experiment. Now, I don't know how the YouTube algorithm is going to affect the display of this video, but I'll export this video at 60 frames per second. But if you notice something unusual, it is because on the video on the left, which is in my main console, like I said before, I use a hardware to extract the video, and that only extracts the video at 720p, so the aspect ratio is different. And as well, it only captures the video at 60 frames per second. I can change that. And to the right, I use a monitor capturing software, which I can't change it, but it only captured video at 30 frames per second. And I tried to change the aspect ratio on the emulator, but I didn't see it. So I'm just gonna, from all the comparisons from the videos, I'm gonna use the default settings that comes as soon as you download the emulator and run yourself. So that's the comparison over here. The main difference between the comparison, if you notice, 60 to 30, there's 1 millisecond difference. And that 1 millisecond difference, it seems like what's causing the video to look slightly off. So given error of 1 millisecond, it matches perfectly. And for some quick clarification, this 1 millisecond difference is referring to this video. You're gonna see 1 millisecond difference between both of them. But the cause of it is pretty much happens because might be one frame difference between both of them. So as you see from the video, every 2 frames from 60 frames per second is equivalent to 1 frame from 30 frames per second. Meaning if both of them start at 0 and they match evenly, then the video should be able to display the same. However, if one of them start on a odd number and you try to match it with an even number, so if the 60 frames or the 30 frames starts at 1 and the other video starts at 0, there's always going to be this offset between both videos that might cause this actual 1 millisecond difference within the video. And to make the comparison, as you see the Legend of Zelda logo appear, the Triforce is gonna rotate, it's gonna be on the front, and then the title Legend of Zelda is gonna show up, and then the Triforce is gonna move to the back. So between the Triforce being on the front and moving to the back, that's 1 millisecond difference. So that's how I align the console video to the emulator. So if I align this perfectly, that's how I get the alignment as close as possible. And of course, it is in different frames. So meaning that the also is going to give the illusion that's a little bit faster, but in reality, it is the same thing. So you're going to give yourself a 1 millisecond difference with an error. A high accuracy emulator, as the name suggests, is an emulator with high accuracy. So that means it's going to be a lot of less visible glitches. And what I mean by visible glitches, it could be like a sound not playing, or a shadow not being displayed on the screen, or let's say something even minor than that. Let's say you shoot a bullet and it's going a pixel more to the right or a pixel less to the left or something like that. So something visible. And since it's a high accuracy emulator, it's going to show up a lot less to even sometimes not at all. And we give those type of emulator a label of high accuracy. Alright, now for the middle accuracy comparison, I'm going to be using the console version with the middle accuracy emulator, which is the no cache SNES. So let's just play and compare the videos. Alright, so if you watch both videos, you may have noticed a big difference. But as far as frame goes, it is pretty much identical to the console and to the high accuracy emulator, the SNES 9X. But the major difference is the flashing part, where the no cache SNS or the no cache Super Nintendo flashes a green light on the screen. And to be nitpicky, the last frame is blue, but you only notice in the green color. And I just want to let you guys know, when I ran it on my computer, this emulator with the ROM, it actually displayed the red-blue as the console plus the green. So the console only displays the color red and blue. However, on the no cache Super Nintendo emulator as well, the SNES 9X, going back to check, it does display a shade of green on the flashing part. So that's a low accuracy error based on the console video that I extracted. So now let's just go over what a middle accuracy emulator is. A middle accuracy emulator is right in between the low accuracy and the high accuracy emulator. It has a fewer glitches than the low accuracy emulator, but still has a little bit of problem here and there. Alright, so now let's compare the low accuracy emulator. And the emulator you're going to be using is going to be the ZNES. So now let's play both videos playing side by side. Alright, so if you remember from the website that said the ZNES plays the Triforce a little bit faster. I think the article said 40%, something like that. And it's clearly noticeable. You do notice a difference when the ZNES and the console plays side by side. One finished faster than the other. And you can see the whole frames getting a little bit out of sync as is. So that's a low accuracy error from a low accuracy emulator. And as well, it does display the flashing green light that you see from the other emulators from the middle and the high accuracy emulator. So if all that is said, let me go over what a low accuracy emulator is. A low accuracy emulator is an emulator that has a lot of glitches, but the main goal is to be able to run. So performance overall. And they generally are for new emulators that just begin. I remember when the PlayStation 2 emulator, the PlayStation 3 emulator, the PSP emulator just started. And I remember they showed a few games that was able to run with a lot of glitches. So they tend to be those kind of emulators. And normally they just go back to it and try to work on it to make as accuracy and as runnable as possible. But the main goal, even from the start, is to be able to run your emulator, to run the games on your emulator. So for the Psycho Accuracy emulator, we're going to be using the BNES. So let's just compare both videos side by side first. Now that's pretty much a perfect emulation compared to the original console. The frame is pretty much identical, given the one frame give or take. And as well, it doesn't display the green flashing from the all other previous emulators. So it's pretty much higher than all the other ones. But Psycho Accuracy does not mean it's higher in terms of glitches. It means it's accurate on the cycle. So let me just go over what a Psycho Accuracy is. A Psycho Accuracy emulator is an emulator that tries to emulate the components by its clock cycle and then later synchronize it at a single resolution. So think of our Stella emulator, which not only trying to emulate the other components like the TV, which could actually at any point, if you remember, it would right click and like stop over here, so it would stop the bin right over there. So it's emulating the bin of our CRT TV. It also was emulating the 6507 chip, so you like jump to this part of the code. So it's, and then later on synchronizing all of those at the exact same resolution. So that's what a cycle accuracy emulator is, and that's what the Stella emulator is. Of course, it takes a lot of more processing power. However, it doesn't mean that it is 100% let's say high accuracy. It means that it's emulating just the cycle, not the visible glitches from the video graphics and so forth. A sub-cycle accuracy is a bit more complicated. So let me start by saying that all CPUs, all chipsets has a clock on it. And that clock's going to produce a signal, a pulse, or a wave, or whatever you guys want to think about it. And that wave has a high point and it has a low point. So going up on the high point is called the rising part, and going down for it is called the falling part. So to have a cycle accurate emulator, like the one I mentioned before, you're going to have to add both of them so it can be fully synchronized. Otherwise, you're going to come up with some precision errors as far as synchronization goes. And a good example is the Z80 processor, which is the processor for the Mega Drive or the Genesis, as well as the Pac-Man arcade game, the first ones, which all of the instructions happens during the rising part. And instructions pretty much are loads or stores, all the parts that we work with the Atari, the same thing. And you know, by working with the Atari, all those instructions take at least 2 clock cycles, and some of them can take 3, 4, or 5. So if you start with an instruction on the rising part, and it is an odd number instruction, so you're going to have to wait a little bit more for the falling part, for the wait signal. So it's going to offset. It's not going to be fully synchronized, as you already can see on this example. So it might be half a cycle earlier to a half cycle later, depending on the instructions. So that's pretty much what a sub-cycle accuracy is. It's just not accounting the time difference, because some of them just use one single beat for all of the wait and the instructions. So that is what a sub-cycle accuracy is. So let's go over the last 2 types of accuracy pretty fast. One is the chip accuracy, which, as the name suggests, is trying to emulate a chip within a board. And a good example of that is the EverDrive 64, which has a anti-piracy security chipset on it that's being simulated, because all of the Nintendo 64 games have the chipset to combat anti-piracy. And the older EverDrive 64 did not have the simulated one, so you actually had to take out those chips out of old cartridges from other games and put it on their EverDrive cards. But the newer one is all simulated. And that took care of, now you can play any game of those, all Nintendo 64 games on your Nintendo 64 console. And the other type of accuracy that we have is called DICE, which tries to emulate old arcade games or the Magnavox Odyssey, which did not have those system, I believe, did not have a CPU, or the architecture is a little bit different. So in the case of the Magnavox Odyssey, we're trying to simulate gates, those logic gates instead of the CPU. Of course, the CPU is made of many logic gates, but you're trying to just replicate the gates itself, so how electricity would flow. So you're trying to solve pretty much a problem on the go. So that takes a lot of hardware power just to run those games properly. And that pretty much cover all the type of accuracies that there is. So I'm going to put a description on the link from all the resources the sites that I found. Alright, so that's pretty much cover all of it. In the next video, I'm gonna go over how we can take our game, Combat Disc, or your game, whichever one you made, and actually run it on a Atari 2600 hardware. So that's gonna be fun. So until then, see you guys. Bye.